Okay, it is now 8 o'clock and we're going to start a lecture. Wow, it's been an interesting week with lots of technical issues, but I'm happy to say that we've got this working today, and also I have a website now that's kind of being slowly put together for us. So if you go to www.cohar.ca, and you can click on courses and then click on MAE 113. I've already put up a couple links already, the assignments, video links, and some review videos as well. So okay, so what are we doing today? We're doing section, I believe it's 6.1, and it's the antiderivative. And the rules of integration. Okay, so remember when I was talking about earlier in this course, we had two problems that calculus is involved with. Let me grab a pen. So we have this. Okay, and some sort of curve like this, and we had something that was like the tangent problem. So there's kind of the tangent. This was the tangent problem that we had. And from there we actually came up with the idea that the slope with tangent is the derivative. So what's the other problem that I introduced at the beginning of the year was we have some curve like this, and the question then became, what's the area under the curve? And that becomes what we'll call the area problem. And surprisingly enough, these two problems are connected. And we're going to have a little look at what that relationship is. So what I'm going to do is I'm going to kind of define the idea of what this area problem is. So again, I'll just draw these axes. And the problem kind of goes like this. I have some curve. So this curve y equals f at x. And this curve also, I think it's important for me to state, at this time it's a continuous function, and it's also positive. And we draw some kind of boundaries here, beginning at, say, around here, and we say here. We call this A, and this is B, and this is the line x equals A, and the line x equals B. And we want to know what this area is. And they'll call this kind of like the region R. So the problem becomes of what is that value? So that's basically it. It's very simply stated. There's nothing else that I need to do. So let me move on to the next sheet here. So we're working on that. Can't put too far up. And so let me just start with my example. So this is my example. And the first thing that I want to do is, well, first is sketch the region under y equals 2x plus 1. So immediately we know that that's a linear function. It's just a straight line from 1 to x. So what I want is find the area function. And also, let's compare the derivative of the area with the equation of the straight line. Okay, so let's just kind of move that up. So that's the problem. I'm just going to move the sheet to the side here. Okay. So we first sketch it. Okay, and we know that it's 2x plus 1. So it's got to start at about 1, say about here, and it's got to go up. Let's say 3 here. There's 1, so it needs to go up here through that point. Lovely. Okay. And so we need to go from 1 to x. So it's got to go from here to say x. X is just a variable. It's just arbitrary. So let's just say about here. Okay. Okay. So is everyone able to hear what I'm saying? If so, somebody just say something in the chat window just to make sure that you can hear me. Okay, perfect. Thank you, thank you, thank you. Good. So I have this, and we got a straight line. I think we can figure out how to do this area. So what we can do is we're going to use some basic geometry. So I have the area. Now, we can break this up into, again, we're always trying to figure out how to do something simple. So what we can do is we can actually break this up into 2 pieces here. I have a right angle triangle here, and then I have a rectangle here. The rectangle here, that's x minus 1. And over here, I've already figured out what the height is. Over here is 3. So that's what I can do. I can do 3 times x minus 1. So that's this rectangle here. And then the triangle here. Again, here's the base, which is x minus 1. and here is the height. Now that height is going to be 2x plus 1, but we also want to remove the 3 down below here because I've already included it. So that means that it's 2x plus 1 minus 3, so that makes it minus 2. Now remember our formula for a triangle. We have base times height, so it's base times height divided by 2, so it's 1/2. So it's 1/2 times the base, x minus 1, times the height, which is 2x minus 2. Okay. Now, we just simplify. So I have 3x. It's good that I see that people are chatting in the window. Make sure that everyone can hear what I'm saying. Okay, so I'll expand that out. So I have here the x times x 2x, so that's 2x squared. And then I have the minus 2x. I'll switch pens so that I can color code this. Let's use orange. So I have minus 2x and then plus 2. Okay, so that means that I have 3x minus 3 plus... I mean, I'm writing out a lot of steps here, so you don't, if you are comfortable with your algebra, you don't have to show all this stuff. Again, I'm just taking it slow, because again, it's probably the first time a lot of people have seen kind of the integral problem or the area under the curve problem before. This isn't usually taught in high school. So I'm almost done. I keep simplifying it so that I have x squared. Oops, my pen slipped. 3x minus 2x, that's just 1x. And then minus 3 plus 1 gives me minus 2. Okay, and that's the formula for the area under the curve from 1 to x. Now, it says for part B, compare the derivative of the area function with the equation of the straight line. Okay, well, we have to take the derivative then of this area. So we've done A, and now let's look at what B is. So I need to take the derivative of that. So that's 2x plus 1. Oh, wow. That's equal to our original function here at the top. So that's interesting. So it turned out that the derivative of the area function was the same as the original curve. So maybe I'll write that out. Let's see. So in this example, we saw that the derivative of the area function is the same as the original curve. Perfect. So wouldn't it be nice if we could somehow establish that link between the derivative of the area and the actual original function? I think we can. So what we'll do is we'll do something very similar to what we did originally, which was we'll draw some curve, and so let's see. We'll define. So let A of x be the area under the curve, y equals f at x. Now remember that this is continuous and positive, so it's above the x-axis. Okay, and we're going to go from little a to x. So let me draw that out. So we have this. Something very simple. So we have 0, and we're going, this is our x-axis, and here's our y. And some curve like that. Okay. And this is y equals f at x. And we start at, say, right around here. And what I'm going to do is probably pick right around here. We'll call this x. So this area in here, that is a of x. Now what I'm going to do is I'm going to use that idea that we had previously of limits that we were using in the derivative. So what I'm going to think of is just a small little shift in the x right around here, let's say here. And so at that point, this is x plus delta x, which means that this sliver right in here is delta x. Okay. So at this point right here, this is P, and we're going to call this, say, Q, and this is, I have a point here, we'll call this R, we'll call this S. And we have the same idea again. We can actually create a trapezoid. So that's what we're going to do. We're going to find the area of this trapezoid here. And let me just call this is point X, and this is F at X. And at Q here, this is X plus delta X, because that's right here, comma F at X plus delta X. So it's just a little nudge over in the right-hand direction, just a delta X amount. And if we look at that derivative, what we want to do is look at that small change. We let that change of delta x go really small. So we want to look at the change. So in here, this is delta A, because it's the change in area, or the change of x. So change of area over the change in x. And what is this difference between here? It's all the area up to this point, and then we subtract all this area up to here. So it's going to be all the area up to x plus delta x. So all the way up to here minus up to this point up. So right here. That might confuse some people, so let me just the right over here. If this was my, here's P and here's Q. This does all the area up to this point. And what this one does right here, here's P and here's Q. This one does all the way up to here, so that when you subtract the two, you're just left with the area in here. So that's what this whole thing in the top is doing. Okay? And then We want to get this very, very small. So let the delta x go to 0, and we get kind of that thin slice. Okay. So this area in here, I'm going to color that something with lime green. So this lime green area, we can actually approximate that. So by using the trapezoid. So a trapezoid, let's see here. So there's kind of a trapezoid, and if I can remember correctly, this is usually called h. This is the height. If I kind of spin it this way, this is usually what people see it as. There's the trapezoid, so there's the height, and then you usually have I don't know. Let's call this A, and this is B, and then that area is equal to A plus B over 2 times the height. So I spin it around. I'm going to apply the same formula to this one right here. So I have that this area is approximately equal to, so I need to do the height, and in this case really we're looking at it sideways, so this is a delta x, and then I need A, which in this case is, well, let's do the B. It doesn't matter which way I do it, but let's do it this way so that I can use f at x plus delta x plus f at x all over 2. So now I can substitute that in. So this is my cloud. La, 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 la. There we go. So dA of x is equal to the limit as delta x goes to 0. And so in the top part, I get delta x times 1/2 f at x plus delta x. All I've done is just brought this 1/2 in front. So just don't panic. I haven't done anything completely weird. I just brought that there. So I have the delta x 1/2 f at x, f x plus delta x plus f at x divided by delta x. Okay, so this cancels. So I'm left with, as I'm simplifying this limit, 1/2 f at x plus, there we go. Now I can actually take this limit. So this limit here, that actually goes to 0. So then I'm left with, remember I don't have to write the limit now that I've taken it. So it's 1/2 f at x plus f at x and f at x plus f at x, that's equal to 2f at x multiplied by the 1/2 leaves me with f at x. Wow. So yeah, we were able to show that the derivative of the area is equal to the original function. So that's how we tie it together. That if you're looking at the derivative, that's the slope, and the derivative of the area is actually equal to the original function. Okay, so I was able to show you that there's some connection between the area under the curve and, say, the derivative. So then the question kind of becomes, what kind of functions can I somehow reverse the derivative? Is there some way that I can get back to the area of the function? So, without having to do all of this. And the answer is yes. But it involves us to look at some patterns. So let's, we've shown that the derivative of the area function is equal to the original curve. So let's just make this a little bit more concrete, because let's say that you want to find the area under the curve y equals x squared from x equals 2 to x equals 4. So quickly we can sketch that out. What it's asking for is something like this. So there's y equals x squared, and from something like here's 2 and up to 4. So we know that the area under the derivative of the area is equal to the original function f at x, which means that in our case here it's x squared. Now we need to figure out what will give us this basically, if we differentiate this function, say ax, what gives us a prime? And basically we know that it's going to be something like, I don't know, we don't know what that is, but it's got to be something where we know that if we took the derivative of it, the degree goes down by 1. Because if we did something like x cubed, and we take the derivative of that, that equals x squared, but also the 3 comes down in front. So we know that it's got to be something like x cubed. But if we have the x cubed here, we have this 3 in the front. So what we need to do is divide by 1/3. So now that if we take that derivative, d by dx of 1/3 x cubed, then when we bring the 3 down, this decreases by 1, so that I have 3 over 3, that equals x squared. So that's the correct one that we want. So we have to have that 1/3 x cubed. The other problem that we face when we're doing something like this, trying to find what will differentiate it, is we're missing a constant. So for instance, if I differentiated this dx x cubed plus 3, we know that that's equal to 3x squared plus 0. So in this case there's a 0 here, but it means that there's probably a constant here. So that's what we end up having to write here, is plus c. C is a constant. We don't know what it is yet. So this only applies if the function is continuous and positive. Yes. For now. We're very careful about, in math, what we're talking about. And what ends up happening is if the function is negative, if it goes below the x-axis, actually they'll have, quote, negative area. So you'll have to subtract from that. So that's to avoid that complication of the negative area, we're just going to strictly work with positive stuff right now. Okay. So we're going to do this right here. And we actually do have an initial condition. So the initial condition is, now if we just had nothing, if there was no area, that would mean that it's right at this point right here, just a equals 2. So that's what we'll do. The area at 2 is equal to 0, because that means that we've brought our bar right really close to 2. So it's actually equal to 0. So that means, therefore, 0 equals 1/3 x cubed plus c. And, oops, I should have put in the 2. So I'll just write that in the next line. 1/3 2 cubed plus c. That's equal to 8/3 plus c. And so that's negative 8/3 equals c. So our area function then is 1/3 x cubed minus 8/3. Uh-oh, it's just doing a circular loading symbol. Okay, is anyone else having issues? Okay. Yes, I'm checking the health of the stream. It seems that good. You just have to exit and come back in. Don't worry, it's a good time to always have coffee. Wow, that is strong. So did I make any mistakes? That's, make sure that I'm plugging it back into the original function. Yeah. 2 cubed, or sorry, 2 cubed, yeah, is 8, right? 2 times 2 is 4 times 2 is 8. Good. Oh, yeah, so we haven't finished yet, because the original says find the area under y equals x squared from 2 to 4. So now that we've figured this out, we've got our function here. Therefore, the required area is a of 4, which is equal to 1/3 times 4 cubed minus 8/3. And so 4 cubed, 16 times 4 is 64/3 minus 8/3. And is that 56/3? I hope so. I thought I had written it out, but yeah, it is 56 over 3. Okay, good. Somebody just said no. Fraz02. What is the no in response to? I'm not sure if I made a mistake or... Oh, okay. I'm good. Thank you. Right. So this is kind of a lot of, I'm not a fan of kind of this guessing and trying and figuring out. And also, maybe we need a little bit better notation when we're doing something general like this. So that's what mathematicians come up with. They have a notation for this. So just to kind of start to generalize. So this was kind of our original problem. So let's do introduction. Here's the notation. So again, we have y, here's x, and some curve, and we go from a to b. Here's our curve, y equals f at x. So what they did, just similar to what we do here, all of these, what we do is we are taking really, really small slices. And the reason when Leibniz was coming up with this notation, he saw this as we're splitting this up into smaller and very, very small rectangles, and letting those the width of these rectangles get very, very, very small. And so we're adding up an infinite sum of rectangles. And so what he thought of when he was coming up with the notation is he used an elongated s. And it kind of looks like s was standing for sum. And what we do is we use this curly s, that's the integral sign, and we say that it's the integral of this f at x. The dx is our differential, which is kind of the width. So this tells you that you're going to be integrating with respect to x. So that's what this is. So this is integrating with respect to x. This is the integral, and it's a long s for sum of rectangles. And we have one more piece of information that we need to somehow jam into this notation. And so we need to be able to say, like in this case from here, we said that we had the curve. So there's the curve right there. And then, oh, maybe we should actually try to write this out here. So this would be x squared, just like that. I need to tell you that we're going to be finding the area with respect to x. And then in this case, we have to tell it from 2 to 4. So we usually put it here at the bottom from 2, which is the bottom, to 4. And same thing with here, if we're going to be arbitrary, we have going from A to B. So it's A to B. And we give this a special term. Oh, and I might as well copy what we found here before. So (56 over 3). We'll check that again later. So this is a special So this is an integral, and in particular, this is called the definite integral. And these are kind of called the, I should also put here, maybe in a different color. These are the limits of integration. Basically, it tells you to go from where to start from A and end at B. So we have the definite integral. Then you'll be like, oh, okay, well, why are we calling it something called integral? Well, because we'll also have the indefinite integral as well. So we have the indefinite as well. And there we go. We'll just write this again. And notice there's no limits of integration. So usually what you'll find is when you have a definite integral, like we had up here, you'll get a number. So the definite integral yields a number. And in this case, without these limits of integration, this just yields a function, kind of like a generic function, kind of like this one right here. So this would be the indefinite integral. So for here, if we wrote, actually no, because there's an initial condition. So we don't. But this will yield a function. I should also be careful with this part right here. It's not always the case, because if these aren't numbers, then it will also yield a function as well. But this is kind of in general. So this kind of, if you had something like 3 to the 4 of x squared, this would definitely yield a number. But sometimes you'll have something like this, where it's from, say, 0 to x of 1 over, let's say, t squared dt. And if you notice in this case, this is a definite integral. There's limits. However, there is a variable in here, and so it would yield a function. So I have to be very careful about what I'm saying. So this would yield a number, and this yields a function. Okay. Okay, so from our last example, we had that the derivative of the area of x squared, and we found that the actual area of the function was 1/3 x cubed plus c. And so I'm going to give you a general formula. So this is important. In general, if I'm integrating some function x to the n with respect to x, then it's equal to 1 over n plus 1 x n to the plus 1 plus c. Remember, constant. So lots of examples. You can use x squared, which we've already done. That's equal to, so it's x 2 plus 1, and then 1 over, we have 2 plus 1, so that would give us 1/3 x to the 3 plus c. The other one, we can do x cubed dx. Again, the exponent goes up by 1, and we have the fraction in front as well, plus a constant, and so on and so forth. So now I have to also mention that this is for n not equal to -1, because that is a special case. But there's other things that we can look at, say x squared, so we can do like this, and we can rewrite that as x to the -2, and then when we integrate this, so we have x, so it goes up 1, and also 1 over the exponent here, so that's -1, so that equals minus x minus 1 plus c, which is equal to -1 over x plus c. What else what other things could do for integration? That we don't have to think too hard about. Well, do you remember the exponent function? We have the exponential, so remember that if we took the derivative of e to the x, that's equal to e to the x. So again, we have another rule. So if we take the integral of e to the x, and to make sure dx, that is also equal to e to the x plus c. So we actually have another rule right there. Right, because the derivative of e to the x is itself e to the x, so if we integrate it, it's just equal to e to the x plus c. Okay, so I've got to keep these in order. Is everyone following along okay? Good. So we have some other properties. Other properties of the integral, let's say, I'll use k. So the integral of k, f at x dx is equal to k f at x dx, where k is some constant. It's a constant. So basically what this says is just very similar to what we did for the derivatives. If I had the derivative of a k times f at x, that k, I can pull this constant in front of the derivative. Okay? And I can actually show this. So here's a little proof. Suppose that f at x is the antiderivative of f at x. Or that is capital F prime at x, so the derivative is equal just to f at x. So then, if I take the derivative of c of the integral of f at x dx, that's equal to derivative of d by dx c, and that's equal to the antiderivative, right? So that's f at x. And since this is a function, very similar to our rule up here, I can do the same thing. So I get c d by dx, f at x, capital X. And if I take since f at x is the antiderivative, and I take the derivative of it, I get back to my original c of f at x. So what I've actually proved here, in this case, is that c of f at x, right here, is an antiderivative of c of x, c of f at x, or that is d by dx of c of f at x is equal to c of f at x. And putting that all together, oh, I'm sorry, I switched here, sorry. I don't know why I switched to C, but C of f at x dx. Okay, so why is this important? Why is this first property, this c f at x dx, equal to c of... Why is this important? Because I can actually now do an integral like this. Okay? Which means that because of this, I have this 9 here, which is a constant, and that 9 can actually come out in front of the integral. And now I can integrate this just as like I had previously, using my rule here. The integral of x to the n is equal to 1 over n plus 1, x to the n plus 1. I've already done that here, but it's x to the third. It goes up by 1, and then 3 in the denominator, plus c. But 9 divided by 3 is 3x cubed plus c. And similarly, we can also do something like 10x to the minus 3 dx And again, this property allows us to pull that 10 out in front of the integral. So I have 10 times the integral, and so I have x, this goes up by 1, so minus 2, 1 over minus 2 plus constant. 10 divided by 2 gives me 5, so it's minus 5x to the minus 2 plus c, or you can rewrite that as minus 5 over x squared plus c. Okay, so that's the first property. The second property. If I have the integral of f at x plus g of x dx, the second property says that I can split that integral for each of the terms inside of the sum. So the integral of f at x dx plus the integral of g of x dx. And also the same thing applies for the minus. And I think, yeah, the proof is very similar. It's me just differentiating on both sides, and I prove it that way. So I'll skip the proof on that one, but basically, yeah, just take the integral on both sides. And here's the examples. So if we had something like 9x squared minus 10x to the minus 3 dx, that's equal to the integral of 9x squared dx minus the integral of 10x minus 3 dx. And we've already done that before. We already did it up here. So this is equal to 3x cubed. I have minus 5 over x squared plus a constant. So there's the first example. Okay. So what I'm going to do is apply the second property to this. So I can break this integral up into 3 separate integrals. So the integral of e to the x dx plus the integral of 9x squared dx minus the integral of 10x dx. We know that the integral of e to the x is itself is still just e to the x plus 9. And now I'm applying the first property here, so I can actually pull out this 9 in front. So I'm taking the integral of x squared dx minus 10 times the integral of x dx. So again, I integrate this. So it goes up a degree to x cubed. I take the reciprocal, so I have 1 over 3 minus 10. This goes up by a degree, and I also have to put it in the denominator as well, plus the constant. 9 divided by 3 gives me 3x cubed, and then I have 10.5, so 5x squared plus c. Okay. I need to take 5 minutes to give my voice a break, so just stand by and we'll resume in 5 minutes, okay? So let me just write that down. So that'll be at 9:07. Okay. Thanks. where can we find assignment 9 solutions? I have them written out, but I haven't. I'll have to figure out a way to get them scanned. But let's see. Oops, that was section. Oh yeah, that was section. There's 5.5. There's 5.6 and 6.1. All right, so I have to go steal a scanner from someone. So I'll have to go figure that one out. But yes, I do have solutions. And yeah. We're just trying to find equipment. So I'll do my best to find a scanner. Okay. Right, so let's start up again. Probably need a new piece of paper. Okay. So you remember a couple of lectures ago, so you remember that I proved that the derivative of ln absolute value of x is equal to 1 over x. How do we do that again? Right, so we can do it this way. So just as a refresher, we have f at x is equal to ln of x. And I can rewrite this into the exponential form, which is x is equal to e of f at x. If I take the derivative of both sides, so that's equal to 1 on this side. And I use chain rule on this, so it's the derivative of the outside function, which is just e to the f at x, times the derivative of the inside function, which in this case is just f at x, so it's f prime at x. And that is equal to x. So I'm left with 1 equals x f prime at x, or that f prime at x is equal to 1 over x. So I had defined that ln x was the inverse of the function y equals e to the x. So and I showed you that the derivative of ln x is equal to 1 over x. I can also now show you that a different definition for ln of x, and it's actually in terms of the area under the curve as well. So we start off with the function y equals 1 over x. Of course, we know that that function is continuous and positive on the interval 0 to infinity. So just kind of draw that in. There we go. That's y equals 1 over x. Again, this is a vertical asymptote right here, y equals 0. And this also is y equals 0, this is the horizontal asymptote, and x equals 0 is the vertical asymptote. So, we have the area A of x. And so what we want to find the area under y equals 1 over x from 1 to x. Okay, so the required area is this shaded area here, and we also know from previous discussion that the derivative of that area is equal to the is equal to the original curve, which is 1 over x. So there it is. And we choose the antiderivative to be capital F of x is equal to ln of x. Remember, so if we take the derivative of ln x, we get back to 1 over x. So that's perfect. And a of x is equal to f at x minus f at 1. And in this case, it's ln x minus ln of 1. But we know that ln here, just because of the inverse. Remember right here, this is e to the x. This is ln x. That here's the point 0, 1. That this has to pass through 1, 0. So this means that this is equal to 0. And so a of x is equal to ln of x. And what we are saying here is, therefore, if x is greater than 1, the natural log ln x is the area under the curve y equals 1 over x from 1 to x. So I think I could write this as from 1 to x of 1 over t dt is equal to ln x. Why am I using this t? It's a dummy variable, because when I need to do the integration, if I did something like that, from the limit from 1 to x of 1 over t dt is equal to ln of t. So there's my t, and my limit is from 1 to x. And it's because of my area. I know that I have to have, I'll substitute in for t for each of these x and 1. So it goes from x minus ln 1, and and that's 0. So again, that's ln x. Okay, so let me just pull out another piece of paper. The next thing I kind of wanted just to kind of summarize, if we had some function so if we took the derivative of this curve, we drop down a degree and we get a quadratic. So we've gone from cubic to quadratic. And if we want to integrate, we have to go up a degree. So when you're differentiating, you're going down a degree. And if you are integrating, going up a degree. Okay, so remember when we were talking about higher order derivatives, we talked about position, and then if we took the derivative of that, we got velocity, and if we took the derivative of that, we got acceleration. Okay, so so if you had the position, there's a kind of our original function, and then we took the derivative of that, well, we got velocity, right? Velocity is the rate of change in position, and acceleration, that's the second derivative of the position. So again, we had position, we differentiate it, we get velocity. If we had velocity and we differentiated that, we got acceleration. We can actually go back in reverse order. So if we started out with acceleration, you could integrate that and get the velocity. And if you had the velocity, you could integrate that to get the position. So I have to illustrate why. You remember when we were talking about we had why those constants of integration. So for instance, if I had some position function, so this is a position function, and let's say it's defined by s of t, 4t squared plus 9t plus 10. If I took the derivative of that, or that's now the velocity, what I get is 4 times 2 is 8t plus 9. Perfect. What if I went backwards? So this is me going down. What if I want to go back up? So in this case, let's start with the velocity function. So I have v of t is equal to 8 of t plus 9. Then if I want to integrate that, I have t squared, right? And I need to divide by 2. I have the 8 plus 9. This is still a constant, so it goes up a degree as well. So 9t plus c. So in the end I get 4t squared plus 9t plus c. But notice this is the constant. But I need more information. As I'm integrating, I'm kind of losing information. So as a, so yes, as you notice, when I have a constant, we just throw that away when we're differentiating. But now as we're trying to go up, we're trying to do integration, I have a constant that I don't know. So this needs more info. So for instance, let's say that we're told that the initial position, so s of 0 is equal to 10, then I can put 10 into here, which is 4 and 0 squared plus 9, 0 plus c. Those are all equal to 0, so c equals 10. So therefore, s of t is equal to 4 of t squared plus 9t plus 10. So that's why we have to have this constant. We lose kind of some information when we're differentiating. So if we're going to integrate, we need to add back these constants. And without any information, we have to leave a c. Now, if there's more information, for instance, they tell you that the integral at a particular point is equal to a certain value, then you can figure out what that constant is and get your final function. And in the textbook, these are called initial value problems. Okay, let's see. I think before I go, I'll do 2 more examples and we'll call that a day. Okay, so we're going to evaluate. So we're going to do the integral of 2x plus 3 over x plus 4 over x squared. So again, using our property, what I'm going to do is I'm going to break up this integrals into separate pieces. So I got 2x dx plus 3. I'm going to write this as 3x to the minus 1 dx plus the integral of 4x squared to the minus 2 dx. So this is property 2 that I used, and then I'm going to use property 1 to bring out these constants in front of the integral. Okay. This one's fairly easy. So the integral of x, so again, it goes up a degree, and I divide by what the new exponent is, plus 3. This is the special case here. So again, that's the integral of 1 over x dx. That is equal to ln of x. So that's the only thing that you kind of have to worry about when you're doing kind of the power rule with the integrals, is if there's a minus 1, you have to use ln. And that's why when we were talking about this earlier, I had to add that, which was if I have the integral of x to the n dx is equal to 1 over n plus 1 x to the n plus 1 plus e, provided that n is not equal to 1, not equal to -1. If it is, then we have to use that special rule, which is the integral of 1 over x dx is equal to ln of x. Okay. And I have 4. Okay, so this goes up by 1, so minus 2 goes up 1, so that becomes -1. And -1 plus c. Alright, so the 2's cancel, so I'm left with x squared plus 3 ln of x minus 4 over x plus c. Okay. So I'll do an evaluate again. 2 e to the x minus x cubed dx. So again, I can think of this as I'm taking that integral and applying it to each term. So the integral of 2 e to the x dx minus x cubed dx. I can pull out that constant in front by property 1. So again, oh, I shouldn't have done that. Okay, anyways, I was integrating that already. But the integral of e to the x is just e to the x. That's easy. And there's our final answer. Now, those are indefinite integrals. What do we do if I have something crazier? So, for instance, let's say that this is x cubed, and I wanted to find the area under the curve from 0 to, I don't know, let's say 3. What does that look like? Well, here's a question that could pop up on the final exam. You know, what's that area? Like, express that as an integral. So the first thing that you'll have to do is, there's the integral from 0 to 3. We have x cubed dx. So that's telling me that I'm taking the integral with respect to dx. So the way that I would write this is you take the derivative, or sorry, you take the integral. So it goes up, the exponent goes up by 1. And you also put that same exponent in the denominator here in front. And you don't have to worry about putting a constant here, because we're going to be integrating from 0 to 3. And we start from the third, so we substitute those values into here. So I get 1/4, 3 to the 4th, minus 1/4, 0 to the 3rd. So again, what that is doing is, this first part here is taking all the area up to the 3rd. The second part here is taking all the area, but it's only up to 0, so it's there. And so I'm left with the area between 0 and 3. Ooh. So if I think of 3 to the 4th, that is that 81? I'm sure someone will tell me. 81 over 4 That's 0. And can I reduce that? Nope. So there's, for instance, how I would calculate something like that. Maybe I should try one more just to show you, just to illustrate that. So I'll do x cubed again, but I'll do it from, say, 1 to 3 this time. So I'm going from 1 to 3, x cubed dx. So that's equal to 1 over 4x to the 4th. I'm just copying from here. And I'm going from 1 to 3. So again, the third would be all the area up to 3. So 1/4 times 3 to the 4th minus, and then I need to subtract the area here up to 1. And that final answer, what it should give me, is between 1 and 3. So that's what this is doing right here. This is what this is doing here. And hopefully, I have 81 over 4 minus 1/4. So it's 80 over 4. And that is what this is. So what I recommend you do, now that you've seen integration, is to try some of those yourself. Just pick up the textbook. And you already have some of these exercises. For number 1 through 4, it says verify directly that f is an antiderivative of f. What this basically says is this capital F, that's the antiderivative. What you need to do is just differentiate that. So for instance, I can't write in the book. So for instance, I have something like f at x equals 1/3 x cubed plus 2x squared minus x plus 2. So it's telling me I need to differentiate that. So d by dx of f at x. Hopefully that gives me f at x. So when I integrate, or sorry, when I differentiate, so I'm going back down. So I got 2, and this is 2 by 2/3 plus this 2 comes down in front, so it becomes 2 over 2 minus, that's just 1, and that's a constant. So hopefully, nope, I made a mistake. So what am I doing wrong? Okay, so when I differentiate this, the 3 comes down, and this becomes 2 plus. When I differentiate this, the 2 comes down in front of here, and that becomes 1 minus 1. So I'm left with x squared plus 4x minus 1. And that's what I have in the textbook here. I'm going to say be very careful at this point, because people will mix up differentiating something and integrating something. Very similar to this, and you'll get a mess. So be very careful about what you're doing. Remember, when you're differentiating something, it's x to the n. So that becomes n x n to the minus 1. And when you're integrating something, x to the n, provided that n is not equal to minus 1, that it's 1 over n plus 1 x n plus 1 plus c. Okay, so for exercises kind of 1 through 4, or whatever from the assignment, you just had to take the derivative of f, and capital F, and show that it's the same as little f. Then you'll have integrals. These are the indefinite. There's no limits of integration on these. And you can pick any of these, and basically using properties 1 and 2 and your power rule for integration, you'll be able to do most of these. And when I say most of those, because most of these are power rules, except for like e to the x. Again, the integral of e to the x is e to the x. What else? Be careful if you ever see something with a minus 1. I don't see any yet. No, I don't see any. There's something interesting here. If you're going to do an integral, say the integral of the square root of x plus 3 over square root of x, again, you just have to change those into exponents. So if you're to do something like that, the integral of square root of x plus 3 of square root of x, you can rewrite that so that you get x 1/2 plus 3x to the minus 1/2 dx. Then again, same thing. Apply your integral to each part. And I'm just going to bring out that 3 in front. So x, so I have a half plus 1. So 1/2 plus 1 is equal to 3/2. So 3/2. Then I have 1 over 3/2 here, plus 3. And when I integrate this, I have minus 1/2 plus 1. So that becomes just 1/2. So that's 1/2, 1 over 1/2 plus c. So that equals, so I have 1 over 3 over 2, and that just flips, so that I have 2/3 x 3/2 plus 3 times, that's 1 over 1/2, so that just flips to become 2 over 1 x to the 1/2 plus c, and just rewriting this out. so that should be enough to get you started. I am going to track down a scanner and hopefully be able to scan some of those solutions for you. And if you have any questions, make sure to send me an email, or we'll figure out something. We're all in this together with this COVID-19 scare. So make sure you wash your hands, don't touch your face, and basically follow a lot of those rules that we were talking about earlier in terms of social distancing. Try to keep space. Well, I guess you guys don't have to worry about that, but for other people like me who are on the outside here, we're having to keep away from everyone. We're washing our hands, and hopefully we can quote-unquote flatten that curve. So hopefully it's not going to follow a logarithm, an exponential growth. Remember, we were talking about that when we were talking about that earlier in terms of the functions of the exponential. Hopefully the COVID doesn't look like that, which is exponential growth. But hopefully what we'll have is something like this, a logistic curve. And remember, I asked you about that, the inflection point. What does that mean? So this is the logistic curve. And what does that mean? It means that that's when we're starting to see a decrease in rate of infection. So hopefully we can flatten that curve and to avoid that. So stay healthy, and again, if there's any questions, make sure that you send me an email. You know my email address. I'm not going to say it out loud because there could be other people watching. If you are stuck with this, I would recommend you can play this back. I'm going to save it, and hopefully you'll be able to access this. Okay, thanks very much. I'll see you tomorrow.